Hi, thanks all for joining. My name is Stephen Toub. I am on the .NET team at Microsoft. I'm super excited about .NET 10, and I'm super excited to be talking with all of you about the performance improvements that have gone into .NET 10. Now, as many of you, or hopefully many of you are aware, every year I've taken it upon myself to write a blog post covering many of the performance improvements that have gone into that release. I'm not a YouTuber. This is my best impression of .NET Bot being an influencer and reacting to all the exciting things happening in .NET 10, as exemplified by this blog post, which you can see has a pretty small scroll bar here. And if I were to print this to PDF, my machine says it's about 250 pages. That speaks to the wealth of performance improvements that have found their way into this release. It also speaks to the impracticality of, I think I have 25 minutes here talking about 250 pages worth of material, which covers something around 300 PRs that found their way into .NET 10, specifically relating to performance. And I should note, out of those 300, about 25% of those came from folks even outside of Microsoft, from all of you. So thank you to all of you that helps contribute to making .NET 10 the amazing release that it is. Since I can't cover all 300 of those PRs, which is also only a subset of all the PRs that went into making .NET 10 an incredibly fast release, what I decided instead to do is just pick a handful of improvements and focus on just those highlights. They're not even necessarily the best improvements, the fastest improvements. They're just interesting improvements. Hopefully, it'll give you a little taste of what .NET 10 brings to bear, such that as soon as we're done, you all run to download .NET 10 and update all of your apps to use it, because it really is the fastest release of .NET to date and super, super exciting. So with that, why don't we dive in and we'll take a tour through some of the improvements that show up. Now to start, I want to start with a topic referred to as de-abstraction. Now, in any modern programming language, programming environment with the compiler and language and libraries, we're often dealing at a pretty high level of abstraction. And you can see this in .NET with things like IEnumerable. We get to write nice little for each loops over any collection and let the compiler and libraries and runtime figure out how to optimize that as best as possible. Unfortunately, these layers of abstraction often come with costs. And so we rely on the libraries and compilers and runtime to remove those costs as much as possible, to de-abstract. And while previous releases of .NET have done a lot here, .NET 10 gets even better, to the point where a lot of the overhead just evaporates and goes away. So I want to give some examples of that. So let's open up Visual Studio. Here I have a very basic benchmarking program. Now, I want to preempt this by saying, or preface this by saying, you should be using benchmark.net to do benchmarking. Do as I say, not as I do. I generally do benchmark.net for all of my benchmarking activities. However, the way benchmark.net achieves the great results that it achieves is by taking a very long time to run your tests over and over and over, and then do statistical analysis and throw out the outliers and figure out what the real signal is and get you down to sort of the real nanosecond level accuracy. But it also means that for demo purposes, it's not particularly exciting. So instead, what I'm doing purely for demo purposes is I've got a little console app and I'm just doing the naive thing. I'm capturing before I start how much memory I've currently allocated. I'm starting a timer. Then I'm iterating some number of times, running my method under test. I'm stopping the timer. I'm seeing how much memory has been allocated thus far. And then I print out basically the difference. So how much time has elapsed and how much memory has been consumed. And so we're just going to do our very simple benchmarking by putting benchmarks into this test method. So let's start by just choosing a simple little type. And since I have a stopwatch up here, let's just use the stopwatch. So I'll say stopwatch start new, stopwatch stop, and then I'm just going to return the elapsed time, which means I need to make this a time span. All right, so we've got our little method. We're testing to see how long it takes to allocate a stopwatch and start it, stop the stopwatch, and then return the elapsed time. So these are the overhead of doing this kind of benchmarking. So let me switch over to the console here. Now I've got this project set up to be able to run tests against .NET Framework 4.8 or 4.8.1 or whatever the latest is on my machine against .NET 9, which was the previous release of .NET Core, and .NET 10, the brand new release. So let's try running this on .NET Framework 4.8, and you can see it's taking about 50 nanoseconds and allocating about 40 bytes. That's fine. Let's try it on .NET 9. So I'll change this to run on .NET 9. Now we're still going to see it taking allocating 40 bytes, but we can see now instead of about 50 nanoseconds, now we're down to closer to 40 nanoseconds. So we already saw basically 20% improvement just going to .NET 9. Now we go to .NET 10, and the big improvement we see here is rather than 40 bytes, we see 0 bytes, and it's also down to closer to 30 nanoseconds. How is that happening? Well, .NET 10 has gotten a lot better at being able to do escape analysis, meaning it checks to see whether this stopwatch instance that has been allocated, whether it's stashed away somewhere. Is it stored into a field? Is it returned out of this method? If the JIT can prove that this object never escapes, then it can stack allocate it, basically as part of the memory that is being stored on the stack frame for this method call. It can just make it a little bit bigger and use that extra memory to hold the stopwatch instance. And as a result, we're able to eliminate all of that additional pressure on the garbage collector, on the GC heap, and our method runs even faster. And this applies not just to stopwatch, of course, but to a whole bunch of things. Let's say I want to change my method to instead take a couple strings. Let's say string A and string B. Let me pass in A and B here. And then I'm going to do something which I think is pretty common. I want to be able to for each over, like do the same operation for both A and B. So I'm going to for each over a value in, and to make this easy on myself, I'm going to create an array so that I can easily iterate over both values that were passed in. And then just to do something with this data, let me create a sum of maybe the length. Yeah, that's good. And I will return the sum. Let's change this to int. All right, so now we're testing to see what happens with this string array allocation. So let's go back. We'll run this again on .NET Framework 4.8. Sure enough, we can see that there is this 40 byte allocation. That's for that array object. We can see it's taken somewhere around 10, 15 nanoseconds. I can run this on .NET 9. We'll see it's a little bit faster now. We may be closer to 8 to 10 nanoseconds, but we still have those 40 bytes. But now I run it on .NET 10, and we're down to 4 or 5 nanoseconds, and the allocation has completely vanished, thanks to this escape analysis and the ability to do this stack allocation. So that's really cool. Obviously, this kind of stuff happens a lot. But one of the most exciting aspects of this is for something that happens throughout pretty much every application you've ever written, and that's enumeration of collections. So let me come up here, and I'm going to allocate an array. Let's say enumerable dot range. Let's do this. Say 100 values in my array, and I'm going to change this method to take an array values, and we'll just enumerate all those values, and we'll sum them up. Now, this method, as written, is actually already optimized and has been for years by the C# compiler. So if I were to copy this method, and let me go to SharpLab, paste in this method here, and look at the code, we can see that there's no for each loop showing up here. There's no IEnumerable or IEnumerator. The compiler has basically lowered it almost exactly as if I had written this to instead be a regular for loop. So if I were to copy this method, and I'll just add a test2 here. There we go. And I'll say for I equals 0, I is less than values length, I plus plus, and then I want to add in values sub I. And we compare these two methods. We can see they're almost identical. There's just an extra little copy being made of an integer value, but otherwise these are identical because the C# compiler is lowering this method to effectively be the equivalent of this method. So if I go back to my benchmark over here, I want to pass in values. and I run this on .NET Framework 4.8, we'll see that there's no allocation happening in that test method because as we saw in the sort of decompiled version of the C#, there wasn't an enumerator at all. It was just a for loop. And we can see it was taking about 50 nanoseconds. If I run this on net 9, we'll see it's better because the JIT is just better. And we can see we're still at 0 bytes and we're at about 40 nanoseconds instead of at about 50 nanoseconds. And I would see basically the same thing if I ran it on .NET 10. But now let's go back to our program. We're going to make one little change here. We're going to change this int array to instead be IEnumerable of int. And if I do that, and I were to copy and paste this method back over into SharpLab to see what this looks like, now we see that we actually do have, this eventually comes up, there we go. We see that I do actually have use of the enumerable and enumerator. I'm calling get enumerator, and in most situations, this is going to need to allocate an enumerator. I've got a try finally block, which before .NET 10 wouldn't be inlined. Now in .NET 10, it can actually be inlined. And I've got this move next method and current access, which are a lot harder to devirtualize and therefore inline because I'm going through this abstraction. Let me go back to my code here. We're going to run this now on .NET Framework 4.8. Previously, this was taking what was about 50 nanoseconds, I think we saw. Now, just by changing that int array to IEnumerable event, we can see it got about 10 times as expensive, and we're allocating 32 bytes. If I change this to .NET 9.0, we'll see that it gets a lot faster. Now, instead of 500 and whatever nanoseconds, now we're at about 190 nanoseconds, so 3 to 4 times as fast, but we're still allocating. Now, if I change this to .NET 10, now we're at another 4x or 5x faster, and we're allocating nothing. And we can see that this happens not only just with arrays, but with other collections. So I could change this to say toList, right? And if this were a list of T, and I were to copy and paste this into SharpLab, we can see if we look at this, what this decompiles to, we're using the strongly typed struct enumerator of list. So there shouldn't be any allocation here. And in fact, we can see if I run this on .NET Framework, there we go. We're not getting any allocation. It's taking about 300 nanoseconds. If I run this on .NET 9.0, we'll see it gets faster still. About, what was it, 5x faster just by upgrading to .NET 9. And we'd see something similar on .NET 10 as well. But now if I change it to IEnumerable, we're going to go back through that abstraction path. So now I run it on .NET Framework 4.8. We're no longer at 50 or 500 nanoseconds. Now we're closer to 700 nanoseconds, allocating 40 bytes. If I run this on .NET 9.0, we'll see it gets faster, but only about 200 nanoseconds. So still way better than it was on .NET Framework, but not close to the value that we saw when it was just the raw listed int. And we're still having our 40 bytes allocated. If I now go to .NET 10, it gets about twice as fast still, and we're at 0 bytes. So really, really cool work happening in the JIT here to eliminate this overhead that'll show up all across pretty much every application you've ever written. That speaks to some common collections like list and array. And so you might wonder, does that only apply to list and array? And the answer is no. This applies to a whole bunch of things. Now, we had to make some tweaks to list of T, and in particular to its enumerator type to get the biggest bang for the buck with regards to the JIT work. And we've made similar changes to other collection types. So let me switch back over here. Let's try a different collection. Let's try stack. And I'm not even going to focus on the de-abstraction at first. I'm just going to use stack event. So let me come back down here, and we're just enumerating a stack using its strongly typed enumerator. This should be very fast. So let's run this on .NET Framework 4.8. You can see it's about 500 nanoseconds and 0 bytes because we're using the struct enumerator. I can run this on .NET 9, where there have already been significant improvements. Now we're about twice as fast. And I can run it on .NET 10, And it's not just twice as fast. Now it's 10 times as fast as .NET Framework. And that's just using the improvements to the collection itself, to stack itself. But we can then double down on this with the de-abstraction support as well. Let's run this now on .NET Framework 4.8. You see now we're up to about 800 nanoseconds. And can run it on .NET 9. We're better at about 300 something nanoseconds, but we still have our 40 bytes of allocation. I run it on .NET 10. And now we're super, super close to it was about 50 or 60 nanoseconds we saw when we were just doing it raw, and 0 bytes, eliminating all of that overhead. We can do it with a queue as well. Let's just try it with a queue. So let's try it on .NET Framework 4.8. About 900 nanoseconds. Do it on .NET 9. About 350 nanoseconds. And on 10. We get rid of that 40 bytes of allocation, and we drop down to still even about 3x faster than it was previously, and almost 9x faster than it was on .NET Framework 4.8. And this applies not just to these core collections, but other collections too. Like, let's try a concurrent dictionary. Let's make this a concurrent dictionary, and we're going to select, that looks good. And then we're going to change this to be an IEnumerable of key value pair int. And we'll change that to .value. So now we're enumerating through our collection of int, our concurrent dictionary int. So let's try that. We're going to try this on .NET Framework 4.8. About 1.6, 1.7 microseconds and 56 bytes. Gets a bit better on .NET 9, maybe about 2x faster. Yeah, about 900 nanoseconds, but still with 56 bytes. Now we try it on .NET 10, where we significantly improve the enumerator implementation for concurrent dictionary. Now we're at 140 nanoseconds and 0 bytes. So all these improvements coming together to make for really nice improvements. And I focused here with collections on these enumerators, but the improvements span well beyond just enumerators. For example, one of my favorite improvements in .NET 10 has to do with bit array. So let's come in here. Let's create a couple bit arrays. A bit array is just a collection of bits. Let's say we want 100 bits, and I'm going to initialize all those to be false, and then I'm going to have another one just for fun. Let's initialize them to all be true. And let's pass in our 2 sets of bits here. Come down here, and we'll take bits 1 and bits 2. So I've got 2 bit arrays, and I want to do something with them. Now, the operation that I want to do for this example is compute the Hamming distance. Hamming distance is basically if I have 2 collections and I were to layer them on top of each other, how many positions do the 2 collections differ from each other? So we want to compute the Hamming distance between bits 1 and bits 2. Distance, that looks good. That looks good. I actually want to make this long because we could possibly more. Great. So I've got my Hamming distance, but this is actually not particularly efficient. I'm having to do a bunch of work for every single bit in these bit arrays. But these bits are packed into bytes, and there are instructions in the hardware that would allow me to manipulate the whole pairs of bytes in 1 or 2 instructions to determine how many, to basically the Hamming distance of an individual byte, or of an individual int, or an individual long, or taking advantage of SIMD. Being able to use vector 128, vector 256, vector 512. We should be able to do this a lot more efficiently. Now, as it happens, there's a method on tensor primitives called Hamming bit distance. So really, I'd love to be able to pass in just bits 1 and 2 directly, but I can't because Hamming bit distance takes span. So I need to be able to get a span to the backing store for these bit arrays. Now in .NET 10, I can do that. So let's say if .NET 10 or greater, I want to return, and instead of using bits 1 and 2 directly, I'm going to use collections Marshall as bytes, bits 1, bits 2, and then we'll just fall back to this implementation for earlier than .NET 10. All right, great. Let's check. Yeah, that looks fine. So let's try running this. We're going to run this on .NET Framework. We're at about 500 nanoseconds. And when we run this on .NET 9, we're still doing the same operation, but we're just able to get better code out, and it's going to be much faster, about 3x faster, going from 500 nanoseconds to about 160 nanoseconds. But now if I do it on .NET 10, I've got to get ready with my control C because this is going to be super fast. Now we're at about 10 nanoseconds, all the way down from 500 or 160, because we're able to take advantage of that vectorization under the covers. So just a taste of the kinds of improvements that you can find in .NET 10 with regards to collections. Also with collections, we use LINQ a lot, like language integrated query, LINQ to objects, basically extension methods for IEnumerable that let you do a whole bunch of operations really to easily express them. And then once you've easily expressed them, you really want them to be as efficient as possible. So we spend a lot of time and energy over the years making LINQ more and more efficient. Let's take a look at an example of that. Let me back up here. I'm going to have this take an IEnumerable of int. And let's do something inside here like values.first. So we're just going to grab the first value out of this enumerable. I'm going to pass in values. And up here, I'll do something like numerable.range. We'll take some data. Okay. So I could run this, right? We have some values. We're asking for the first, pretty standard stuff. Of course, I could chain these operations together. So maybe I say order by, and I actually want to order by the negative value. Now, this is where things get interesting. In .NET Framework, this would perform the full order by, the full sort, and then first would come in and select the first result. But that's actually overkill. And in .NET Core, starting with, I don't know, .NET Core 3.0, something around there, a bunch of optimizations were done to pass information between the query operators in LINQ. So order by doesn't just do the sort and give the result to first. First actually sees that it's operating on an order by. And that means that it can actually skip the full sort and just find the minimum. Because if you sort a thing and you ask for the first one, it's going to be the smallest value. So let me make a small tweak here to the number of operations, because that's probably going to be too long. I'm going to bump up the number of values being sorted just to make this obvious. And let's try running this. So on .NET Framework, this order by .first was taking a long time. There we go. All right. So it took about 122, what is that, milliseconds per operation? All right. Now let's try it on .NET 9.0. Now, this is still going to take a while. Actually, it's not going to take a while. It's going to be very fast. We can see that the 122 milliseconds is now down to about 2 milliseconds. And that's because on .NET 9, it was able to apply this optimization that translates an order by .first into a MIT. So these kinds of optimizations have already existed. But now let me change this first to instead be, say, contains, which is not something that we previously taught LINQ how to understand. So now it actually is going to do the full order by followed by this contains operation. So let's try this again. And on .NET Framework 4.8, it's going to take approximately the same amount of time that we saw before. So I think before it was about 122 milliseconds for each of the operations. And this should be approximately in the same ballpark, about 128. Now, if we run it on .NET 9, it's going to be faster because .NET 9 is just a lot faster over across the board than .NET Framework. But we're still having to do that full sort of 1 million elements, and so this still is going to take quite a bit of time. Here, it's about 1.5 times as fast, but still 83 nanoseconds. Now, if I do this on .NET 10, because we're now able to chain that information through to contains, you can see it's like instantaneous, 10 to 20 nanoseconds for something that was previously taking many milliseconds, which is pretty cool. And the same optimization applies to other cases. Let's say I do a reverse. Right? Reverse actually do the semantics that it employs. It makes a full copy of the input and reverses it. So if I try and run this on .NET Framework 4.8, we're going to see that it's not having to do an order n log n operation, but it is making a full copy, resulting in 8 megabytes being allocated. If I do this on .NET 9, we can see that it's about 4 times as fast, but allocating about half as much, but still allocating 4 megabytes. Now I do it on .NET 10, we're able to skip the reverse entirely because it knows that the reverse has no impact on the success or failure of contains. So now it's taking sub 10 nanoseconds and is allocating nothing. So these kinds of improvements just show up when you move to the new version. All right, it's enough of LINQ. There's other improvements there. There's new methods, shuffle, left join, right join, etc. Other cool optimizations, but you can explore those on your own time. Now, we were talking about enumerating. We were talking about LINQ. Those all have to do with searching. Regex is another super common example of wanting to do searching. And in pretty much every release of .NET Core since .NET 5, we have improved the regular expression engine in .NET, and that goes for .NET 10 as well. So let's switch over to actually a different set of windows. Rather than showing more benchmarks, running them on different versions, I thought what we would instead do is take a look at how this shows up using the Regex source generator. For those of you who aren't aware, the Regex source generator was introduced in .NET 7. And at compile time or live in the IDE, it takes whatever your regular expression is and it generates a full implementation of that regular expression in C#. So we can see here I've got an empty regex, and if I look at the code that's being generated for this, it's just matching the empty string, so it's always successful. If I were to change this to be ABCDEF, now we can see that live, the implementation changes. We're first looking for a possible match where we find C or F, so it's looking for this last character that might make up a match. And it's chosen C and F instead of A or D because it's determined statistically that C and F are less likely in common input sources. And then once we found a possible place to match, we're checking to see whether it begins with A, and if it does, try and match B, C, or if it begins with D and is followed by EF. You get the idea. But this is cool because we can now see live the impact that changes we made in .NET 10 make. On the left side of my screen, I have .NET 9. On the right side of my screen, I have .NET 10. So let's start with an example like this. So let's say I've got an expression A star followed by AV. Now this A star is what's referred to as a greedy loop. Greedy means that it consumes as much as it can. And then if you have a backtracking engine like you have with the source generator, if it fails to match what comes after that loop, it backs up, giving back something that it matched to try and match what came next. And then it gives back something else, it gives back something else. Basically, it keeps trying to give back things to satisfy what comes next. And we can see that greediness if we look at the source implementation. After we match as many A's as we can, we have a label here. And we jump down to match what comes next, trying to match either an A or a B. And if this fails, we jump back to that label, we back up a little bit, and we try again. And if it fails again, we jump back up here, we back up a little bit, and we try again, and so on, and so on. But if I were to change this to instead be just A star B, now we notice that this word has changed from greedily to atomically. We still have a loop, but the engine has recognized that there's nothing that the A star could match that would also match B. And as a result, no amount of giving things back from this loop will be successful. And so it can change that greedy loop into an atomic loop, meaning one that never has to give anything back. And that's really nice because it changes the algorithmic complexity of the regex. Now, if we scroll down, we see there's no more label. There's nothing to jump back to. And if the matching of the B fails, the whole match fails immediately rather than having to jump back to something and try again. So we jump at the opportunity to make more and more things atomic because it can significantly reduce the processing time of these regular expressions. So let me give another example. Let me try /w plus. This is matching as many word characters as it can, followed by a math symbol. We can see that this is matching greedily, but there's actually no math symbol that is counted as a word character. So this should have been able to become atomic, but the engine didn't know how to reason about the overlap between Unicode categories. Now in .NET 10, we notice a few things. One, we can see that we get a nice usability benefit. This fairly obscure match a character in the set gobbledygook now translates into match a Unicode math symbol. So that's a nice usability benefit. But we also see that this greedily has become atomically, because the engine has now been able to recognize more and more cases of this where this auto atomicity could apply. We could see that as well if I did say /s followed by a capital S. These are distinct sets. This is a white space and this is anything other than white space. This should be able to have been made atomic, but it's greedy. If I do the same thing on .NET 10, we can see that now instead of greedy, it's atomic. So we're getting these nice benefits. And there's a bunch of places where this improves. There are other improvements in .NET 10 around being able to just remove completely unnecessary work. So let's take an example of, let me say I'm doing, let's try this. So this is a 0 with positive look ahead. So basically we're looking to see if what comes next matches, but then we're not consuming it. It contains an anchor, and it's followed by the word hello. Now, in actuality, this expression is identical to if I had just moved the anchor out of that look ahead. And you notice that by doing so, it changed what was being matched, because previously in .NET 9 and earlier, the engine didn't recognize that this anchor could actually be lifted out of the look ahead. But in .NET 10, it does recognize that. So if I copy this over to .NET 10, you'll notice that I get the same behavior now in .NET 10 as if I had moved it out on .NET 9. And that's really important because we're eliminating a huge swath of work. If I look at what the code looks like for finding the next possible match, we're seeing that it's searching the whole input looking for the string hello, basically the next place to match. Whereas on .NET 10, it's only matching if we're at the very beginning of the string. And that means we're eliminating trying basically all the different possible places and searching through the whole string. We're eliminating one or more potentially very expensive searches through the input. And just for fun, we can see the impact of this. So let me copy out this regex into my program. Go up here and I'll say equal to regex, paste that in. We'll use regex options dot compiled. And then I also need some input. And so for input, again, we're going to do a do as I say, not as I do. You should always cache your HTTP client instances, but for the purposes of this demo, I'm just going to manufacture one. And we're going to grab some data from Gutenberg. Let's do, I think 3200 is Mark Twain. Let's just double check that. Yes, the complete works of Mark Twain. And now we're going to pass in our regex and our input. We'll come down here and we'll do regex and our input. And then I want to return the number of matches. So let's do return r dot matches input count. All right. And again, we're using this anchor inside of this positive look ahead. So let's try and run this on .NET Framework 4.8. And we're at about, 24, 23 milliseconds. I can run it on .NET 9, which already had massive amounts of improvements in the regular expression engine. And we can see that we're about 12 times as fast, going from 24 milliseconds to about 2 milliseconds. But now if I run it on .NET 10, I again need to get my Control-C fingers ready. Because instead of milliseconds, now we're at about 30 or 40 nanoseconds. Because it only has to match the very beginning of the string. So we're eliminating huge amounts of work. One last thing to show, and then we're out of time. You'll notice that there are these little dots here. One of my favorite aspects of pretty much any .NET release is we add more and more analyzers to try and find opportunities to do improvements. And there's an example of such an improvement in an analyzer in .NET 10, where it's recognizing that if you're on .NET 7, I think it is, or newer, you have access to a count method that allows this to be allocation free and do a whole lot less work. So I can just apply that fixer. And I'm able to utilize this count method instead. So with that, I will say thank you so much I hope you all will go and grab .NET 10. I hope you will all upgrade all of your applications to it. And I hope you will all share your experiences with it so we can all see any improvements you have, any regressions you might find, but also learn how we can do even better for .NET 11. Thanks very much.